Hello, this is the Unit 4 review. In this review, we're going to review the topics that we've covered in Unit 4, kinetics, equilibrium, acids, and bases. Periodically, as we go through this video, you may want to pause it so you can think about the answer to some of the questions that I pose, write down your answer, and then restart the video so that you can kind of check your thinking and process each question as we're going through to really help you to learn and internalize and master this information. And so as we're talking about these topics, kinetics, in equilibrium, we're really starting to look at how energy is involved in these chemical reactions. And so if you're looking at these particles right here, what type of energy is involved with these particles? And so if you thought kinetic energy, you are absolutely right. These particles are moving, and generally always particles are moving. We've never gotten to that temperature, absolute 0 Kelvin, where the particles stop moving. And so this would absolutely be kinetic energy. How about this? Take a look at the water there in the reservoir. What type of energy would you say is shown there? If you said potential energy, you are absolutely right. Let me go back one slide. That water has energy due to its position. And so as you now know about those kinds of energy, chemicals also have energy. If they have stored energy, that would be potential energy. They have the potential then to release that energy. If as they're moving, they also have energy. And so when we start to take a look at chemicals, like a chemical reaction, would you say this reaction is endothermic or exothermic? Hopefully you were thinking exothermic. Exactly right. And so if we were to look at the delta H value or the enthalpy value for this reaction, we would get a negative value. You should also be able to take a look at a reaction profile, like a graph shown here, and determine what A, B, and C are, and then what type of reaction this would be, endothermic or exothermic. And so for this one, hopefully you were thinking exothermic because A and B are the reactants. They're going to have more energy than C, which is the product. And so it's sort of like, think about those reactants are rolling down that hill. And you can see that hill there, and they wind up at C. How about this one? Obviously, this is an endothermic reaction. The reactants have less energy than the products, so we're having to push those reactants, A and B, up that hill. How about this one? Can you identify each of the letters? So obviously A and B are the reactants, C is the product, and D is the activated complex. So often times as chemicals react, they have to form sort of an intermediary complex to allow them to become products, and that's what we're seeing at D. And so if we're looking at these kind of chemical reactions, if we wanted to speed one of these reactions up, which one of these would not speed one of the reactions up? If you thought increasing the size, you're absolutely right. Because the other three, a catalyst or increasing the temperature or the concentration, would definitely speed up a reaction. How about the study of rates of reaction? Do you remember that word? Absolutely. If you said kinetics, you are correct. How about energy in food? How do we measure that? So hopefully you were thinking of calories with the big C, which are really kilocalories, and you are exactly right. That is how we measure the energy in our food. Now remember the definition of a calorie. This is a little c, is the amount of energy to raise 1 gram of water 1 degree Celsius. So if we asked you what the calories were, if we had 10 milliliters of water and we changed the temperature by 6 degrees, so our delta T is 6 degrees Celsius, how many calories would be given off or emitted through an exothermic process? And so hopefully you figured out 60 calories, because obviously it was 6 degrees times 10 milliliters of water. Notice I've rounded that 60 off to 2 significant figures by adding that decimal point. All right, taking a look at this one, how many calories in a candy bar with 28 grams of carbs, 12 grams of fat, and a gram of protein? This would be a great time to pause the video once again and determine the number of calories. And so hopefully here you multiplied the grams of carbohydrates by 4, fat times 9, and protein times 4. Then if you simply figure out what each of those answers is and add those together, you will get the calories in the candy bar. And of course, we would round that to 2 significant figures because 1.0 gram of protein is 2 significant figures. All right. We also looked at equilibrium expressions. See if you can come up with the equilibrium expression for this reaction. Now, of course, equilibrium expressions are just gas and aqueous chemical species. And so this one would be the CO, the carbon monoxide, squared divided by the carbon dioxide. And of course, when we're putting that in those brackets, that means concentration. Remember, when we're looking at those equilibrium expressions, what if you have a large equilibrium expression, a large KEQ? And of course, that tells us that we're getting more products forming. And so if we're looking at this reaction, what would shift the equilibrium toward the products? And so as I'm looking at my 5 choices there, obviously I'm going to get rid of V, because we know catalysts have no effect on equilibrium. They do speed up a reaction, but once that reaction reaches equilibrium where reactants are making products at the same rate that products are making reactants, it has no effect. So that would be the first one that I'm going to eliminate. And then obviously, if I look at letter A, if I increased the products, that would just increase the concentration of my reactant. So I'm also going to eliminate A. And now I'm down to B, C, and D. So I've got 2 with the temperature and 1 with pressure. So then I'm going to look at B and try to figure out the pressure. And so I know that my equilibrium will be shifted to the fewest moles of the gas when we increase the pressure. And so obviously that's not going to, B is not going to work. So now I'm between C and D, increasing the temperature. And so that's where we need to look at this enthalpy value. If it's a positive value, so obviously it is endothermic. And so from that, I can figure out what's going to work. And of course, if I increase the temperature, that is going to shift me toward the products. Because this is endothermic, heat is going to be a reactant. And so when I increase the reactants, that is going to increase the products. Another way to think of this is that equilibrium shifts away from the heat when you increase the temperature. Oh, I'm sorry. When we look at shifting the equilibrium toward the reactants to the left, increasing the pressure would do that, as we already talked about, because that's going to go to the fewest moles of the gas, which we have in the reactants. And then, of course, we studied acids and bases in this section of our Chem 110. Acids taste sour. Bases, of course, taste bitter. Sorry, I gave that one away for you. And so which of these is not a strong acid? And this was something that I told you earlier that you probably just kind of need to commit to memory. And so acetic acid here, because this is hydrogen acetate. Since it's acetate with a T-A-T-E at the end, that's why it is acetic acid. Here's some other strong acids that you should have committed to memory. Don't forget that when you have a strong acid involved in a neutralization reaction, if it's involved with a strong base, that would make a neutral salt. But if a strong acid is involved in a neutralization reaction with a weak base, it is going to make an acidic salt. All right, so what about a pH of 9? What would you say about that? If you're saying that, oh, that's pretty basic, I would agree. I would call that moderately basic as well. How about 4, if you have a pH of 4? If you said, oh, that's pretty acidic, I would agree. I'd call that moderately acidic. And then, of course, what is this reaction called? An acid reacts with a base to produce salt and water. If you said that is a neutralization reaction, you are exactly correct. And then figuring out the different types of salts. Now, the way to figure out these different types of salts is to first take the salt and break it into the component ions. So obviously magnesium chloride here, the salt is going to be made from magnesium ions and chloride ions. And so then I've just got to figure out, okay, so my base must have been with the magnesium. So that must have been magnesium hydroxide. And so the hydrogen must have come from my acid, which would be hydrochloric acid, to form this salt magnesium hydroxide. Well, and both magnesium hydroxide and hydrochloric acid are both strong, and so this would make a neutral salt. Let's take a look at this chemical reaction. Can you label all of the chemical species here? And so obviously I have a typo here. This should not be a conjugate base. This is our conjugate acid. Water, remember, according to Bronsted-Lowry, an acid is anything that can donate a hydrogen ion, which of course water can. And the KNO3 would be our conjugate base. It can accept a hydrogen ion. I apologize for that typo and for those animations coming up incorrectly. And we already talked about this slide and how I broke the magnesium and chloride into the two ions. All right, now calculating pH. See what you can do here. Hopefully you use the formula, is that right here. pH is the negative log of the hydrogen ions. And simply plug that into your calculator, negative log 0.000001. And you got a pH of 6, of course slightly acidic. Can you predict the products of this neutralization reaction? Hopefully you were thinking calcium nitrate and water. Calcium nitrate there is our salt, which is also going to be our conjugate base. And then, of course, thinking about what type of salt would that be. So once again, I'm going to have to look back at the acid that I have here and the base and determine their strength. And so obviously it is going to be a neutral salt because nitric acid, HNO3, is a strong acid, and calcium hydroxide is a strong base. Now, it's true that it's not, because of the calcium, it's not as soluble in water as we would like, but for every mole of calcium hydroxide that we dissolve, we're going to get 2 moles of those hydroxide ions. And so that is going to make it a strong base. How about the products of this neutralization reaction? If you said sodium phosphate and water, you are exactly correct. There's our salt and water again. Can you label this reaction with the conjugate base and conjugate acid? And so as I'm taking a look at this, obviously my acid, nitric acid, my base is that hydroxide ion, because Bronsted-Lowry told us that any base is a hydrogen acceptor, so obviously that can accept my hydrogen. Arrhenius said that bases have hydroxide ions. And so there's our conjugate acid and our conjugate base. So make sure that you've practiced that and are able to do those types of questions. How about this one? Can you label the chemical species in this neutralization reaction? And so hopefully you said, as you looked at each one, you figured out that HNO2, hydrogen nitrite, nitrous acid, is our acid, and there is our base, and there's our conjugates as products. And then, of course, as we're thinking about water, we remember that water can dissociate to form what ions? So hopefully you're thinking hydrogen ions and hydroxide ions. Remember those hydrogen ions combine with water to form hydronium ions. And when we're measuring pH, that's really what we're measuring. And so thinking about the equilibrium constant, the KQ or KW is the concentration of the hydrogen ions times the concentration of the hydroxide ions, which equals 1 times 10 to the negative 14, which you can use in your calculator to determine your hydrogen ion concentration or your hydroxide ion concentration. Of course, if a solution has hydrogen ions or hydroxide ions, we can then figure out the other ion or the pH from that. So if the concentration of hydroxide ions was 0.000368, what would be the concentration of the hydrogen or hydronium ions? So hopefully you plugged that right into your calculator and determined that your hydrogen ion concentration was 2.72 times 10 to the 11th. What about the pH of this solution? Now, of course, for this reaction, you're going to need to use the concentration of your hydroxide ions. There's your formula. So simply plug that in, 14 plus that log, and you've got a pH of 11, which we would expect because, of course, NaOH is a base. What if you have this concentration of hydronium ions? So as you are taking a look at that, hopefully you use this formula and simply typed in your concentration to come up with 4.5. So pretty acidic solution there. In the lab that's due, it's actually due in another week, you've got part B of the titration experiment, where you're actually titrating the unknown acid with the base. And so again, this is due in the Wednesday after Thanksgiving. So as you're doing that, If you had 50 milliliters of a 0.1 molar NaOH solution, and that is the concentration of the solution you mix up here, if it was titrated with 13.4 milliliters of an unknown hydrochloric acid, which is a monoprotic, so it's donating one hydrogen ion, what is the concentration of the acid? Now, because you have a 1-to-1 ratio here, you can use the M1V1 formula and simply solve for the molarity 2, and you should get 0.3731 for your molarity. And then, of course, you would need to round that to significant figures based on the numbers you pull off the burette. As you're reading the burette, you should be able to read that to 4 significant figures so that you've got 2 decimal places in your burette reading. Now, for a question like this one, you're going to need to use your stoichiometry skills, because you have 2 hydroxide ions for every hydrogen ion. So when I write out this reaction, so if we're taking a look at this reaction, if we write out the reaction, hold on, there it is. You can see that we've got 2 moles of acid reacting with 1 mole of base. And so when this happens and you have 1 mole of base to 2 moles of acid or vice versa, you can no longer use the M1V1. And instead, you've got to use your stoichiometry skills. So you need to look at the molarity of your base times your volume. Then use the mole ratio from your balanced equation to determine the moles of your hydrochloric acid. Now, if you take those moles of hydrochloric acid and you divide by the molarity, you'll get the volume. Oops, and I guess I did not calculate this volume here and get that calculated correctly, or it's not animating up there. So it would be 0.12 divided by 0.43, which is 0.27 liters. So that'd be 270 milliliters. And here's another one for you in another titration. So already I'm looking, I know that my acid is not monoprotic. It's not going to donate 1 hydrogen, but 2, so it's diprotic. And we've only got 1 hydroxide ion. And so I've got to think about my reaction, because obviously we're going to have a 2-to-1 ratio. And so I cannot use the M1V1. I'm going to have to use stoichiometry to solve this one. And so as I'm doing that, I'm going to figure out the number of moles of my lithium hydroxide. Then I'm going to look at my lithium hydroxide. We've got 2 moles of lithium hydroxide to 1 mole of sulfuric acid. And that's going to give me my moles of sulfuric acid. And then, of course, I'm simply going to take those moles, divide by the liters. I converted 17.6 milliliters to 0.0176 liters, and that will give me the concentration of my acid. So I hope this helps you. I would encourage you to continue to review the vocabulary. Here's all of the different vocabulary words that I mentioned as I went through the PowerPoint this evening. The PowerPoint is also on D2L for you. If you have any questions, please let me know.